Okay guys, so now we are going to talk about chapter 25. It's geometrical optics. Okay, so in a few minutes you will understand why we call it geometrical optics. Alright, so light, what is light? So we always talk about like photons and stuff like that. Nowadays everybody knows what a photon is. But the thing was that the first time when they first thought about it, nobody knew what light was. So Newton was the first person who came up with light must be little particles, right? Corpuscle theory, that light is made up of little corpuscles, that these little particles making light rays, right? And then also, of course, from obvious reasons, from observation, he knew that light goes in a straight line. If it is going in the same medium, it will go in a straight line. So then they made up the theory of ray theory of light. Later you will see that they are also called, there are theories called like wave theory of light, which can explain, for example, colors on the soap bubble and stuff like that. Using ray theory of light, you cannot explain that. Of course, now at the age of quantum, we know light is actually made out of these little particles called photons, right? Which has also particle nature and also have wave nature. So that's, we are getting into quantum mechanics and quantum electrodynamics. But right now we are going to talk about ray theory of light, geometrical optics. So we see objects. When we see objects, the reason we are seeing is because light rays coming from those objects, whether they are originated from the object or reflected from the object, they come into our eyes, right? Then it hit our retina and then we interpret them as, our brain interprets it as an image, right? So that's how we see things. So first of all, we are going to talk about reflection of light, right? When light rays hit a surface, it will reflect. So just like my palm, you see the light from the ceiling is coming, but you can still see it in that direction, right? And the reason is because although light hits the surface coming from that direction, my palm is not smooth. So it will reflect in all kind of direction. So what is the law of reflection? So the law of reflection is actually follow this principle. Let's think about two parallel walls, right? Forget about light for a second. And then you are playing a game and you are standing here and the game is to run and hit this wall and come back to this wall, right? Okay? So what you want to do is you want to hit somewhere on this wall and come back to this point, all right? And then soon, after you play for a while, you will find out that the shortest distance is the one that makes an equal angle with the perpendicular. This angle and this angle must be the same. Incident angle and reflected angle must be the same, and that path will be the shortest. So if you run with the same speed, then that will give you the shortest amount of time. So if you run, for example, like this, and that path will be longer, you can measure it. So actually you can draw 2 or 3 different paths and you will see that the shortest distance is always given by the one that makes equal angle at the surface. Alright? So that's the law of reflection, is like that. And so actually it was first theorized by some French mathematician called Fermat, and what he said was that light will follow the path that will take the least amount of time, called principle of least action. Alright? So anyways, the law of reflection is very simple. Incident angle is equal to reflected angle. So light comes in, let's say this is a mirror, a smooth surface, then it'll be reflected like that, and this angle, the incident angle, then the reflected angle, these two angles will be the same. That's called the law of reflection, so it's not difficult. By using that, you can draw a lot of neat pictures. For example, like how do you see yourself in the mirror? Let's say this is the back of the mirror, I'm shading it, that's the side where you put the mercury in. And let's suppose this is you. Right, so let me see if I can do the same thing. So now, how do you see yourself in the mirror? And the light rays coming from the hair hit the mirror and then come back and hit the eyes and goes into your retina, right? And in order to do that, it has this angle and this angle, they are equal, right? Because it has to obey the law of reflection, right? So behind the mirror, there's no real light rays, but I'm going to draw a dotted line. So it's coming from the hair. So that's how you see the upper part of your face. Then same thing here, the light ray coming from the chin will make an equal angle at the mirror and will be reflected right into the eye. This angle and this angle are equal, go into the eye, so you see the chin. And on this side, there's no real light rays, I'm just drawing that, so that's how you see that, okay? So actually, it's just a geometry problem that in order to see a whole figure, all you need is, you see the mirror that you need, the length of the mirror, you need to see the whole face. Although the face is bigger than this size, you can still see the whole face. So what you need is, you need only half the length of the face. So if you are 6 feet tall, if you want to see your whole body, all you need is a mirror of length 3 feet. Alright? But anyways, we will draw more fun figures later. So now we are going to go to the next problem of refraction. Before we do that, let me talk about, like, for example, I was talking about my palm. So let's suppose, just pretend this is my palm, right? It's a rough surface. Then although the light shines from here, see, you see, everybody can see the piece of paper, right? The reason is because it's a rough surface, so it's going everywhere, right? And the reason is because if you look at it microscopically, the surface is like this, right? Not even at all. But of course, because in the human scale, it's still a very thin sheet of paper. So whenever light ray hits, say light rays are hitting here, there, no matter where it hits, it still has to obey the law of reflection. So at this point, this will be the perpendicular. 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 So you see, the light ray that hits at this point will be reflected in that direction. This one will go in that direction, that one will go in that direction, this one will go in that direction, right? Making equal angles every time it hits. You see, so it goes everywhere. That's why on these rough surfaces, when light hits, everybody can see because it goes everywhere in all directions. If it were a smooth surface, just like a mirror, then let's suppose you have a very, very smooth surface. the light source, light ray come in, then it will go only in the same plane with the same angle, right? And so only one particular angle, from that angle you can see it, but in other angles you cannot see that, right? So now let's talk about law of refraction. So what is refraction? You have seen it all the time, and when you were younger, I'm sure you have played around with it. Like when you put your finger or your spoon in a lemonade glass or whatever, what happens is that you will see that the spoon is bent, right? Looks like the spoon is bent. And that phenomena is called refraction, right? So again, we are going to, actually the principle behind it is what we call the principle of least action. This is not in your book, okay? I'm talking out of a little bit higher level physics. It's called the principle of least action. And that principle of least action, from there you can derive the law of refraction. In your book it will not derive it, it will just tell you, okay? And if you want to derive it, then I can give you a physical example. Think about this. Let's suppose this is a seashore and you are here. And one of your friend is swimming, and let's suppose that person is drowning, right, in water. And you want to save your friend. So the thing is, you run with different speed. V1 on sand, this is sand, and you swim with the different speed V2. Of course, you run faster than you swim. So, what is the shortest path, or what is the path that will take the least amount of time to get to your friend? The shortest distance is, of course, a straight line, but the thing is, what the more important thing in this case is the time that it takes. You want to get there as soon as possible, right? So the path that will take least amount of time is this path. Right? And so again, if I make a little angle, then this is what we call the incident angle, the one with respect to the normal or perpendicular, and that's a refracted angle, theta r. This is theta I. Let's rewrite again, theta r, this is theta I, right? And in order to get the shortest path, then you will get to this formula, not the shortest path, sorry. In order to get the path that will take the least amount of time is this. That is velocity of light divided by speed in that medium. So let's call it VI, and sine theta I will be velocity of light by the speed in the second medium. So let's say R, and then sine theta R, right? Okay, so I can change this to incident velocity and refracted. So this is the velocity in the medium that is coming in, and this is the velocity in the medium that is you are refracting, right? So just pretend like they are light rays, then that's what you will get. And this C by VI is called Ni, and this C by VR is called NR sine theta R. So I stands for incident, R stands for refracted. Now in your book, they will use N1 sine theta 1 is equal to N2 sine theta 2. Doesn't matter, right? One, you use 1 or 2 or incident and refracted, right? I prefer incident and refracted so that you will know which one you are dealing with, and then you are not going to make a mistake. Because if you use just N1 sine theta 1, N2 sine theta 2, then you will get confused and later you will make mistakes, alright? So this law, or this law, which is the same, is called Snell's law. Right? Snell's law. And actually, if you think about it, instead of refracting, if you think about reflection, it'll be the same medium, because when you reflect, something is, let's say like this is the incident medium, then it'll be reflected back in the same medium. So N1 and N2 will be the same, and then it'll show that theta 1 is equal to the same as theta 2, or theta incident will be the same as theta reflected. So actually Snell's law is applicable for both refraction and reflection, right? But for you, all you have to do is just remember this, all right? That's all you need, okay? So it tells you that obviously the path that the light takes in real life, right, in actual world, is obviously this path, which is not the straight line, right? Not the direct straight line from this place to this place, right? This is not it. This is the correct one, right? Okay, so why light choose that? Of course, it's, it take a lot more to explain, you need a little bit higher level physics to explain that. But right now, just imagine like light itself can think, then it'll seek out the path that it'll take the least amount of time to get from one place to another. Okay? Now, you can just Google it, called principle of least time. Alright, so now what I'm going to do is I'm going to draw a little picture for you so that you'll understand how it works. So, I suppose this is a little bit related to one of the problems that I'm going to assign, so pay attention. Let's suppose you are standing here and you are looking into a pool where there's a fish, right? So the fish imagine you are wearing green pants and the water is green, right? And I'm going to draw a fish here. Okay, so the person that's seeing that fish, the light ray from fish is actually going like this. See? So the perpendicular line to the surface is here. So this is the angle of incident and this is the angle of refraction, because the light ray is going from the fish to the guy, right? If this guy is looking at the fish, that's what he would see, right? Because the light ray is coming from the fish to the guy. But if the fish is looking, it'll be different, right? Okay? So if the fish is looking, it'll be different. So you think about that. Now, where would be the image of the fish? Obviously, the guy thinks that the light ray is coming from here, so obviously the fish, the image of the fish is here, right? Okay? So the green one is the image. So that it looks like it's a little bit closer to the surface than it actually is. Alright? That's how you see things in water. So now I'll let you think about how the fish would see this guy, because that's the problem. In problem number 10 that I'm going to assign. So let me do an example. So I'm going to do, oh, by the way, in table 25.1, table 25.1, all the index of refraction, index of refraction for all those things that they measured is in there, right? For flint glass, for diamond, for water, and stuff like that, okay? So when you do the problem, you can look up. So let me do an example problem. The example is example 25.2, page 894. That's example. So they said look at the problem and then look at the picture, and the incident ray or theta 1 is 30 degrees and refracted angle theta 2 is equal to 22 degrees. Alright? And incident or N1 is equal to air, which is 1. It's for air. And they want to find what is N2. Alright? What is N2? So this is a very simple problem. All you have to do is what? N1 sine theta 1 is equal to N2 sine theta 2, or I use NR. So theta I, theta R, and NI, NR, N1 sine theta 1, N2 sine theta 2, or you can use this. NI sine theta I is equal to NR sine theta R. Right? As long as you remember one of them, that's fine, right? Just don't get mixed up. I prefer you to use this because then you'll remember this is incident, this is refracted, right? But if you can remember, that's fine. Okay? Doesn't matter. N1, N2, N1 sine theta 1, N2 sine theta 2, that's also fine. So let's plug it in. What we want to find is we want to find NR or N2, right? So let's use this NR. NR is equal to NI sine theta I by sine theta R. So Ni, which is in air, the index of refraction for air is just 1. Sine theta I is sine 30 degrees. So make sure you put your calculator in the degree mode and not in radian mode, because then you will get wrong answer. And to check, always remember, sine 30 degrees is equal to 0.5. So if you get wrong answer, you will know, because you should remember a couple of numbers. So sine 30 is 0.5. So it's easy number to remember. And then divided by sine theta r. Sine theta r is 22 degrees. So if you plug it in there, then what you will get is 1.33. This is about index of refraction, which is for water. Okay? Right? So that's very easy. Right? Now, the next problem is physically similar, but mathematically a little bit different. So the next exercise is problem 25.3. Exercise, sorry. And it asks you Ni or N1 is equal to 1 because that's air. Theta 1 is 30 degrees, same as before. But this time, the second medium is diamond. So for this value, you have to go look up. And then they want to know the refracted angle. How much is that? So you still use the same formula. So Ni sine theta I is equal to Nr sine theta R. Right? So N2 or Nr you can write. Okay? Or if you prefer, you can use 1 and 2, doesn't matter. Right? 1 is for incident, 2 is for refracted. Right? So in this case, we want this angle sine theta R. So obviously, I need to look up for Nr, and I go and look for diamond, and Nr is 2.419. So Nr or N2 is equal to 2.419. So here, Ni sine theta I divided by Nr is equal to sine theta R. Right? So now we can plug in numbers. Ni is for air, it is 1. Sine theta I, that's sine 30 degrees. Nr is 2.419. That is equal to sine theta R. Now sine 30 is 0.5. So then I can calculate that. So if I calculate that, that is 0.5 divided by 2.419, which is about 0.207, is equal to sine theta R. So now, at this point, in order to get theta R, you have to hit the inverse function in your calculator. Don't forget that. First of all, it has to be in degree mode. If you don't use the degree mode, the answer will be in radians. You have to put it in degree mode, and then you do the sine inverse of 0.207. So theta R is equal to sine inverse of 0.207, and what you get is 11.9 degrees. Okay, so that's easy. All right, so and I'm going to assign you to do problem number 10. Okay, I'll write it up, and as usual, I'll give you 2% credit, right, towards the final. So problem number 10, and so I'll send you by email. All right? Okay? Then I'll do some more problems later for the future. All right. Okay. Thank you.